Okay, so we have now this solution for the case E less than V0. We have as a function of x, for x less than 0, we have a e to the I kx plus b e to the minus I kx. And for x greater than 0, we have c e to the minus kx. All right? Now, let's analyze what this means in terms of the experiment. We have the current towards the right. Okay, so probability current, so for x less than 0, probability current towards, or let me just say in plus x direction, is what? It's going to be h bar k over m magnitude a squared. Probability current in the minus x direction is going to be h bar k over m times magnitude of b squared. So let's look at what magnitude of b squared is. So it's going to be h bar k over m magnitude of 1 plus k over ik divided by 1 minus k over ik. Right? But this is a simple sort of magnitude. I need the magnitude squared. So I can just look at the h bar k over m magnitude squared of the numerator, 1 plus k over ik squared magnitude of 1 minus k over ik squared. So it has a real part and an imaginary part. So it's just going to be h bar k over m. I forgot my a's, right? There's an a magnitude squared here, multiplying all of these things. So a magnitude squared. And the magnitude of the numerator is going to be 1 plus magnitude squared is going to be k squared over k squared. But I also have 1 plus k squared over k squared for the denominator times a magnitude squared. Okay? So to summarize, it's going to be equal to h bar k over m a magnitude squared. So what does that mean? The probability current in the plus x direction and the probability current in the minus x direction are equal to one another. Okay, so we call this, we give this thing a name. Okay, so probability current in the plus x direction divided by the probability current in the minus x direction is going to be h bar k over m b squared divided by h bar k over m a squared. In this case, these factors cancel. They don't always cancel, okay, for all coefficients. For reflection, it always cancels, but we'll also define a transmission coefficient. Okay, so this is 1. So this is called the reflection coefficient. Okay, so 100% of the particles will return back. So if you carry out an experiment now with many particles, as many particles as you like, okay, with 100% probability, all of them will bounce back from this barrier. And that makes sense, okay? They don't have enough energy to go over the barrier. Let's just make sure that we have the nothing flowing into the right-hand side, okay? For x greater than 0, okay, probability current in general, okay, is going to be what, h bar over m, the imaginary part of u star du dx. So it's going to be h bar over m, imaginary part of u is real, so it's going to be c star e to the minus kx. Okay, derivative brings down a minus k, and c e to the minus kx, but everything is real, there's nothing imaginary, so I get 0. Okay, so there's no probability current on the right, which makes sense. Okay, so since probability is conserved, I should get, if everything is being reflected, I should get 0 on the right-hand side. Okay, let's now look at the case when I have an energy larger than V0. So classically, in that case, I would have all particles going toward the right with 100% probability. Let's see what happens in quantum mechanics. So for E greater than V0, let's just draw this picture again. That's my x, that's the V of x, that's my V0, and now my electrons are being shot with an energy larger than V0. Okay, solutions on the left-hand side are the same. So for x less than 0, I again have a e to the I kx plus b e to the minus I kx, just as I had earlier. Okay. So for x greater than 0, okay, similar to the other case, except that I have to be careful with the signs of E minus V0. So minus h bar squared over 2m d squared u dx squared plus V0 u is equal to E u. Now E is greater than V0, so let me just write this so that I have positive quantities. D squared u dx squared is equal to minus 2m over h bar squared E minus V0, right? So E will have the minus sign and so on. So E minus V0 times U. So E minus V0 is now positive. So this coefficient is negative. So the solutions to U are again exponentials, complex exponentials. But this time the wave number, okay, is not k, but it's q. So in fact, q squared is going to be equal to 2m over h bar, square root of 2m e minus v0 over h bar.
Isn't this q?
Q, yes, thank you. Very good. All right, so now I have to do the same algebra that I did earlier. So let me look at the continuity of U. So on the right-hand side, okay, we are not finished here yet. So on the right-hand side, I have U is equal to C e to the I qx plus d e to the minus I qx. But just like on the left-hand side, remember that this A star A was a measure of incident flux or probability. So C here is associated with, okay, so this time it's going to be H bar Q over M times magnitude of C squared is what? Probability flux, well, probability current, sometimes called probability flux, so I'm sometimes using that terminology, but probability current in plus x direction. And similarly, H bar Q over M, magnitude of D squared, is probability current in minus x direction. But what would that correspond to? What would probability flow in the minus x direction would correspond to in the right-hand side?
Like nothing here, because it would correspond to a particle that was sent.
Yeah, okay, so that would correspond to a particle which is being sent from the right-hand side, okay, and it would be a very weird case because it would also, it's just a single particle case, so it would be the same particle actually coming in from both sides, okay. So it is not impossible in the world of quantum mechanics, but our problem is now much simpler. So we are going to choose this d equal to 0, okay, and throw away this solution. Yes?
Also, what about the total probability current of U? I mean, there is some U before
Yes.
it,
Mm-hmm.
and we just calculated the probability current of plus and minus x direction, right?
Mm-hmm.
So, what about the total probability current of U? Does it equal to sum of that?
Yeah, just the sum of these two. In fact, we are just interpreting these things as
When we apply the probability current definition, does superposition?
yeah, okay. We did that, but let me just quickly do that. If you look at U star du for something like this, what do you get? You get U star, which is C star e to the minus iqx, right? Plus d star e to the plus iqx. And then you have the derivative, okay, which is going to give you iq c e to the iqx plus, yes, minus iq d e to the minus iqx, right? And then we'll also need the imaginary part. Okay, so it's the imaginary part really decouples. So you see, when you look at these terms, you are going to get iq times c star c, right? The imaginary part is still there. And then minus iq d star d. And then if you now look at the cross terms, plus c star minus iq d e to the minus 2 iqx, and the other one, which is d star plus iq, okay, c e to the plus iqx. Now you see this term is the complex conjugate of the other, okay? So d star, c star, c, minus iq plus iq minus plus, okay? So this whole thing is real and doesn't survive the imaginary part, okay? So that's why we are taking only the A star A and B star B parts. All right. So continuity of U gives me, so my D is out, so perhaps I'll, okay, just to put a box around it so that I can find it more easily. So if the u is to be continuous at the boundary, I am going to get a plus b is going to be equal to c, right, at x equal to 0. Yes?
So did we choose b equals to 0, right?
Yes.
Okay.
Okay, and then we have the derivative here, which is ik, right? A minus b, just like the previous case, is equal to derivative of this at x equal to 0, which is going to be c times iq. So very similar equations, but let's see what that gives us. So this second equation I can write as a minus b is equal to, dividing through by ik, q over k times c. So I have a plus b and a minus b equations. So that's nice. I can just combine them. I can just add them. That will give me 2a, and the b's cancel, is equal to 1 plus q over k times c. All right? So c is equal to 2 over 1 plus q over k times a. So that's our c. Let's also find b. Okay, let me try to squeeze it over here. Sorry for squeezing everything, but I want to keep everything on board as much as possible. So this equation just tells me that b is equal to c minus a. So if I collect them over the same denominator, this is going to be 2 minus the denominator, 1 plus q over k, divided by 1 plus q over k times a. So I have 1 minus q over k over 1 plus q over k times a. Now you see the magnitude squared of this is not going to be 1, right? Because this is all real, and I have to be careful. All right, so let's see what that is going to give us. Yes?
Could you explain why d is equal to 0?
Why d is equal to, because d corresponds to a term which implies a probability current in the minus x direction on the right hand side. So it corresponds to a probability current in this direction, which I don't have any reason to expect. Okay, I'm sending particles from the left. They may be bounced back and sent towards the right. Okay, and if I am not sending the same particle from the right hand side also, then I don't really have any probability current there. All right, one thing that's missing in this classroom is a clock. Okay, so where are we? So let's look at the reflection coefficient. Okay, so what is R? R is, remember, the current, which is h bar k over m magnitude of b squared divided by h bar k magnitude of m a squared. Okay, so this is the incident wave, that is the reflected wave. Okay, so these pieces cancel, and I have b squared. Where's b? Okay, this thing here. So it's going to be 1 minus q over k over 1 plus q over k, everything squared, and a is cancelled. Okay, I'll define, okay, so this is the reflection coefficient. I'll also define a transmission coefficient now. So it's going to be T, and it will involve the current, again probability current. This time the transmitted current, okay, the transmitted wave. So that, remember, has that magnitude. So it's going to be h bar q over m c squared divided by the incident current h bar k over a squared. You see the h bar over m's cancel, but the q and the k do not cancel. Okay, so keep this in mind. If you have a potential difference between the left-hand side and the right-hand side, you'll have these, okay, wave numbers different on the left and on the right, and they don't just cancel. So don't forget to put those in. So what is C magnitude squared? It's going to be 4 over, okay, 4Q over what? 1 plus Q over K squared
Times K.
times,
There should be a K in the...
yes,
in the-
okay, sorry. After telling you not to forget this, I forgot it myself. Okay, so Q over K. So let's see. First of all, let's see if probability is conserved. What is R plus T?
1.
Well, let's see. Okay, trust but verify. That's always a good sort of policy. So in the numerator on the left, I have 1 minus 2Q over K plus Q squared over K squared. That's the, and in the denominator, I have 1 plus Q, 2Q over K plus Q squared over K squared plus 4Q over K, which comes from that. Okay, so now if I combine this 4Q over K with this minus 2Q over K, okay, so what happens? This just makes this a plus, right? So this becomes equal to 1. So indeed, the sum of the transmitted and reflected probability currents is always 1. This is just conservation of probability. What does this transmission look like? Well, let's just try to put in these variables, Q's and K's, etc., into the equation. So Q over K is, remember, Q is square root of 2m e minus e0. Okay, so it's square root of 2m e minus v0, and K is square root of 2m e, right? So divided by h bar in both cases, but they cancel. So it's going to be square root of 1 minus v0 over e. Okay, so the transmission coefficient is going to be 4 times this, 1 minus v0 over e, divided by 1 plus, okay, this q over k again, square root of 1 minus v0 over e squared. Yes.
I believe immediately before this 2Q divided by K, there is a minus instead of plus.
Yeah, but that's part of the algebra. It was minus. Sorry, I did this in one line. Okay, so this is minus, and I add this to it. Okay, so this makes this a plus. Okay, so Okay, my shorthand algebra. Okay, so what do we have for transmission as a function of the energy? Okay, so this is what we are after usually. So this is the energy is something we can adjust, energy of the incoming particle. It comes in, it has a certain probability to be transmitted, and the maximum transmission that you can have is 1, since you cannot create particles during the scattering. And we know that until energy becomes equal to V0, okay, that's the case when energy is less than V0, and we found out that transmission was 0, right? Everything is reflected. So I have this transmission curve equal to 0 until my energy gets to the classical, okay, limit on which the particle can go on the other side. Now, once I reach V0, I can use this equation. So when V0 and energy is equal to V0, I still have 0 for transmission. And as energy increases, you see this term becomes smaller and smaller. So what happens? Why did I get a 4? No, that's okay, because it's squared. Okay, sorry about that. So for E equal to V0, this curve starts from 0 and it increases. When E becomes very large, this numerator just becomes 4. The denominator becomes 2 squared, which is also 4. So this curve just approaches, okay, 1 like that. Okay, so if you send particles with higher and higher energy, the probability of transmission becomes higher and higher. But unlike the classical case, it's not automatically 1, okay, as soon as you exceed V0. Classically, if you have a hill to climb and if you have sufficient energy in the beginning, once you reach the top with 100% probability, you pass to the other side. Whereas in this case, that's what we have. Now that we have solved this problem, you see, if you want to, yes?
So for the classical mechanics, this transmission function is discrete? I mean,
Yes,
0 and
yes,
1.
yes,
So
that would be
unit step
say,
function.
yeah, it would be a step at V0, okay? All right, now that you have found this, you can actually go back, and if you want to send a Gaussian wave packet across the barrier, you can do that, right? So suppose, okay, so we have actually solved the problem for this Hamiltonian, right? So it is in 2 pieces, one piece where the energy is less than V0 and one piece where the energy is greater than V0. But in any case, for this problem, we know the solution on the left-hand side and on the right-hand side. Now, suppose you really want to solve what a Gaussian does near this potential. So here I have my Gaussian, and it's in the form e to the minus x over x0 squared with some normalization. I better give it some momentum, otherwise it's not going to move, right? If it doesn't move, it will still spread out and some part of it will pass the barrier, but I want it to move towards the right. Okay, so I have something like this. Let me use some other variable here, okay, some normalization. Okay, alpha will stand for anything, okay, so suppose that's my normalized wave function. Now, what I want to do is I want to write this in terms of the eigenfunctions that I have found. But that's very easy because I know how to convert this into a g of k e to the I kx. So okay, 1 over, let me put 1 over root pi under the g of k. Okay, so this is the expansion, and this e to the I kx, remember, are waves that are moving towards the right. So if I want a solution, I must match all of these parts. So this was my psi at x, say 0, right? But now I want to also put in the whole wave function. I want to write it in terms of the whole wave function. So if I want to generate also this reflected wave, okay, so it's not going to be that simple, but since there was a question about it, let me just clarify this. Okay, so I'm going to get this object moving, g of k over 2 pi e to the I kx minus I e k t over h bar. Okay, that's the motion of the wave that's moving towards the right. But I'm also going to get the b and the c parts, right? So this coefficient is like my a part. Now I'm going to have a b part here, which is going to be e to the minus I kx plus I e t over h bar. Okay, so this is going to be the form of the solution. Where am I? I forgot my dk. So I'm going to have this thing here. So what is this b? Okay, this b is going to be a discontinuous function. Okay, so this b of k is going to be equal to, I hope I haven't lost all of my a's and b's and such things, but I think I can recover. So b of k is going to be, let's see, 4 k over ik divided by 1 plus or minus ik for k squared h bar squared k squared over 2m is less than v0, or it's going to be equal to this thing here for k over q 1 plus q over k. In any case, I don't guarantee any correctness in any of this. For h bar squared k squared 2m greater than v0. Okay, so it's going to be some discontinuous function as a function of k here. Okay, and then you just develop this. So this is only the left-hand side. On the right-hand side, of course, you have to write a similar equation.
Also for the left-hand side, shouldn't we put somewhere jk divided by 2 pi divided by a?
Yeah, okay, so this a, instead of this a, we are going to put a g here. Okay, and g is what you found from the Gaussian.
I couldn't understand why a equals to gk divided by 2 square root of 2 pi.
Okay, so we have solved the problem when I have e to the I kx on the left-hand side. But now I want to solve the problem when I have g of k e to the I kx on the left-hand side. Okay, so g of k is the magnitude of the wave with wave number k.
My mistake, I lost that part, sorry.
Okay? So you start from the Gaussian, you find your g of k. So if it's not a Gaussian, it's a different g of k. Obviously, your solution will be different. Okay, so this is now associated with the coefficient A that we had. Okay, because it's the coefficient of e to the I kx, but now I have to add over all types of waves. Here we are looking at a single k, that's what makes our problem easier. Here we have a single k, so for that single k we can solve the problem. So if you want to solve a more general case, that's what you would do. In practice, you would probably, if you want something that complicated, you would probably want to solve it numerically. You probably wouldn't do it analytically, but formally this is what you would do, yes.
Still, I couldn't understand how did you write this pi x.
Okay, just remember that we found this solution for a e to the I kx, okay, incident on the system. System is linear, so what would happen if instead of a, I had a g of k? So a would go to g of k, okay, and b would then be equal to, where's my b? Okay, so b is something, okay, let me try to write over here. B is some function of, okay, k over ik divided by 1 plus or minus, okay, I don't remember the details, k over ik squared times a. Okay, so if a goes to g, then b goes to this thing times g. Okay. So it's just a consequence of adding all or expressing my initial condition in terms of the solutions of the Hamiltonian. My Hamiltonian now has a somewhat more complicated solution. It has one solution on the left, another solution on the right, etc. But I can still expand any function, any general function like this Gaussian, in terms of these eigenfunctions. Okay? And once I expand them, I just put in the time dependence, and that's how they behave. So the procedure has not changed. What we have found here is the solution for a system in which the incident particle has a certain definite k. So that makes our solution easier. Okay? Yes.
These B's are going to be the same things we have found
Yes.
here, right?
Yes.
So I think it's very wrong what you're.
Yes, it's probably very wrong. Yes.
If
Yeah.
if a goes to gk, why did we write gk over
Hmm?
square root of? If a goes to gk here,
Yeah.
why did we write gk over square root of 2 pi?
Well, this is the general case, right? So I'm just going to convert this to a. I just replace this with a. Okay? So that's all I do.
Is there going to be a square root of 2 pi in the B2?
Yeah, of course, there will be all types of details. Okay, so I just sketched the solution for you, and I think I now regret it that I did. Okay. Okay, so let me just quickly summarize where we were last time. The tunneling problem is a problem in which we have a potential energy, okay, as a function of x, which is in the form of a barrier between 0 and a, okay, and 0 potential elsewhere. Okay, and has value v0 here, so this is our v of x, right? So if you like, v of x is equal to v0 for x between 0 and a, and 0 otherwise. All right, and we have various cases that we have to study. depending on what the energy of the incident particle is. So if I have the energy of the incident particle coming in from minus x less than V0, then the type of solutions that I'm going to get here on the left is going to be e to the plus or minus I kx, okay, linear combinations. In the middle, it's going to be linear combination of e to the plus or minus capital Kx, and to the right, we are expecting solutions which go like e to the I kx again. No e to the minus kx because I don't have any particles incident from the right. Okay, so I am going to get, okay, so let's also specify what these k's and k's are, small case and uppercase. So small k is going to be square root of 2m e over h bar. The capital K is going to be equal to, okay, remember the Schrödinger equation, so maybe I'll just write it down for that case, h bar squared over 2m d squared dx squared u is equal to v0 u, sort of plus v0 u is equal to e u, so that I'm going to get d squared dx squared u is equal to v0, okay, 2m v0 minus e over h bar squared, okay, for the case when v0 is larger than e, times u, so that this u is going to be a linear combination of e to the plus or minus k x's, and k is going to be square root of 2m v0 minus e over h bar, right? So, well, okay, I wrote it over there. Okay, so the k here and the k there obviously are the same because the energies are the same, potential energies are the same, so I get the same small k. Okay, so I write down equations which connect these solutions to one another at these boundaries. So at x equal to 0, I want to match the values of u to the left and right of the boundary. Okay, so, well, maybe I should also write down the form of the solution here so that I can use that. Okay, so the solution here, linear combination of these things will give me a e to the I kx plus b e to the minus I kx. In the middle here, I'm going to set this equal to c e to the plus kx, kx, and plus d e to the minus kx. And to the right, I have just this. Let me just skip the variable e, not to confuse it with the energy. So I'll write it as f e to the I kx. Okay? So these are the types of solutions in these three parts of space. So the matching at x equal to 0 tells me if I put x equal to 0, I'm going to get a plus b is equal to c plus d, right? Let's go on. If I look at the derivatives, when I differentiate with respect to x, on the left-hand side, I bring down plus or minus ik, and over here, I bring down plus or minus capital K. So if I want to match u prime, yes? Questions? Okay. I k a minus b is equal to capital K c minus d. Now let's just go to the other boundary. So at x equal to small a, if I match the boundary condition at u, or boundary condition for u, I'm going to get what? C, now I have slightly more complicated expressions, e to the ka, because x is not 0 anymore. So plus d e to the minus ka is equal to the function on the right hand side, e to the I ka. Okay, so this now matches the value at the x equal to a boundary. Similarly, if I just want to match the conditions for the derivatives, I will get, this differentiation will bring down a k, and I'll get c e to the ka minus d e to the minus ka is equal to f ik e to the I k a, right? So 4 equations and 4 unknowns. All right? So we solve these things and we get something, okay? I'm not going to do it. Okay, what are the 4 unknowns? Okay, the A is considered to be known, so B, C, D, and F are considered as unknowns, okay? And I determine them in terms of A. And once I determine them in terms of A, okay, for example, if I'm interested in the transmission coefficient, remember what the transmission coefficient is. Okay, it's going to be h bar over m, okay, times k. Okay, so h bar times k times f squared divided by h bar k again divided by m divided by a squared. So because the potential is the same, the k's are the same, so I just drop those factors. Okay, so it's the probability current on the right hand side divided by the probability current incident on the left hand side. Okay, so this is the transmission coefficient, and I gave you what that was last time, so I'm just going to do that again. I'm not going to go into the algebra. It will be a miracle if I can get this thing right without your help. Okay, so this is going to be 1 over 1 plus sine hyperbolic squared ka divided by 4e over v0 and 1 minus e over v0. Okay, so we just trust one another in that. Okay, and let me at the same time just write down, maybe it's best to put everything on one board. So this is the case when E is less than V0. What happens if E is greater than V0? Okay, if E is greater than V0, the only change in the type of functions, in type of solutions that we get are going to be in the middle, right? So in this case, I'm going to get a, okay, so let me just redraw this shape again. as a function of x. This is v0, and that's 0, and that's a. So the solutions are again going to be the same. I'm going to get a e to the I kx plus b e to the minus I kx here. But now here I'm going to get c e to the I qx plus d e to the minus I qx. Okay, I get oscillatory solutions because now my kinetic energy is greater than the potential energy. So I'm somewhere over here. And because of that reason, yes.
Also in previous class we wrote sin h, just sin h instead of sin h squared.
Okay. H? What's H?
I mean,
Okay, so I have, okay, that's going to come here. And E is larger than V0. Okay? So in this case, I am going to get an f e to the I kx. So the equations are practically going to be the same, okay, except that in the middle part, wherever I had a k here, I'm going to have an IQ. Okay, so we are going to get, in place of k, we are going to get an IQ, and then, of course, sine hyperbolic of an imaginary quantity is the sine function, right? So the sine hyperbolic function, sine hyperbolic of, let's say, theta, is going to be e to the x minus e to the minus x divided by 2, whereas sine hyperbolic, I'm sorry, just sine theta is going to be e to the I x minus, well, these are thetas, right? Sorry, theta, I theta minus e to the minus I theta over 2 then I. Okay, so that's what we have. All right, so the only change from the previous equations to these equations is, instead of having these k's, I now have this IQ. What is Q? Well, just Q is now, maybe I'll do the algebra again. Okay, so in this case I have minus h bar squared over 2m d squared dx squared u is equal to, well, plus v0, u is equal to eu again, just like the previous case. But now E is greater than V0. So I'm going to get d squared u dx squared is equal to minus 2m E minus V0 over h bar squared u. So you see, this is actually the same equation. Here I have written it as V0 minus E, and here I write it as minus E0V. So what makes the difference is that what is in the parenthesis is positive, both in that case, because over there V0 is larger than E, and in this case, because here E is larger than V0. But since I have a negative quantity here now, this is going to give me, okay, U as a linear combination of e to the plus or minus iq x's, where q is equal to the square root of this. So it's going to be square root of 2m e minus v0 over h bar. Okay, so the algebra is the same, except that I'm now going to get a term here, which is going to contain a sine term. Okay, so what happens is that in place of Ka, now this goes into I Q times A. Wherever I see a Ka, I replace those things with IQA. And of course, that means this sine hyperbolic squared now is going to generate a minus sign. So the transmission is going to be equal to 1 over 1 minus sine QA, okay, sine squared QA divided by 4E minus, okay, E over V0. Sorry about that. E over V0, 1 minus E over V0. Okay, so that's our transmission. And I'm going to get two types of solutions depending on whether my energy is less than V0, whether I'm below the barrier. Okay, so this is the case when the energy of the incident particle is less than the peak of the potential energy. Okay, so this is the case when I have quantum tunneling case. Okay, tunneling in the sense that, okay, this particle doesn't have enough energy to go over the barrier, so it constructs a tunnel, okay, through the barrier. Type of argument, the type of naming, okay, and over here I am above the energy limit. Okay, there's something wrong with this expression because, okay, I think this is plus. Okay. That's because I was too hesitant saying that everything goes into that, but there's a Q here which is going to make, there's an IK there which is going to generate a minus sign. Okay, so in any case, let's look at what the tunneling rate, okay, the transmission rate is as a function of the energy. For values of energy, okay, so this T can be at most 1, remember. For values of energy less than V0, okay, this sine hyperbolic is a monotonously increasing function as a function of k. So what I get here as energy increases is the effect of this term is to get, let me just orient myself. So if k is large, okay, so let's look at the limit when k times a is large. Okay, so if I have a thick barrier and a large k, so if I have a large Ka, I have this sine hyperbolic function here, which is going to dominate everything, right? And the sine hyperbolic function goes like e to this object, right? So the large Ka means this sine hyperbolic Ka will approximately be like the first term there. So it's going, the positive exponential is going to dominate e to the Ka over 2, right? If Ka is very large, then sine hyperbolic is the first term, okay, in the expression. So that's what I have. And that term is going to be larger and larger, so it will dominate over this 1. And what I'll be left with is just that term, except that it's squared, so T is going to be equal to approximately, okay, square of that is going to give another 4, so it's going to be 16 e over v0, 1 minus e over v0, but e to the minus 2ka, right? So this term is going to be approximately e to the 2ka over 4, and it will dominate over this term 1, so that 1 will be negligible, and what remains is going to be something like this. Okay, so for values of energy which is small, and when energy is small, k is large. So for small values of energy, I am going to get a large value of Ka, which is going to dominate this equation. And then I'm going to get a very, exponential-like dependence. Obviously, there's other terms here, but these are slowly changing with energy. This is changing exponentially. Okay? And then it's going to reach a certain value. But if I go over V0 now, I am going to get a dependence on energy, which is sinusoidal. And at certain times, this term becomes 0. And when that term becomes 0, I am going to get transmission of 1. So, okay, there will be certain points here as the sine oscillates. So as I go to higher and higher energies, I am going to get closer and closer to full transmission. But even before that, I am going to get certain places here where, okay, so when does that happen? It happens when QA has such a value that makes the sine equal to 0. So that corresponds to n pi, right? So for this is going to be n equal to 1, first resonance, n equal to 2, n equal to 3, etc. So these things are called resonances. Okay? Yes?
Can you explain what is the physical picture behind it? What I mean is that, for example, is there an analogy of this in the classical wave mechanics? Like,
Yes, there's an analogy of this in optics. Okay, so if you calculate, for example, the transmission of waves through an optical structure. So you may have an optical structure in which you have some glass, and then on top of it you put some material, some dielectric material with a different index of refraction. Okay, so such things correspond to changes in index of refraction which look like a barrier, and depending on the thickness, you can block away or transmit certain wavelengths. Okay, so the standard classical example is that of coatings on camera lenses, which when you look at them, you'll see that they look bluish because they tend to reflect ultraviolet. Okay, so on camera lenses, there's a thin coating of some material which results in interference. So this is an interference effect. Okay, so it corresponds to this QA equal to n pi. But if we now go back and see what Q was, okay, so Q is right over here. So the resonances are at, okay, square root of 2m e minus v0, okay, over h bar is equal to n pi, or this is, okay, so h bar squared, n squared, pi squared, I forgot to multiply by a, okay, so this is a times q, divided by a squared times 2m, okay, are the values of E minus V0. Okay, so what does that mean? Okay, let me just finish this. I have this much energy above this tunneling barrier. This energy difference is E minus V0. And these energies correspond to those discrete energies if I were to put an infinite wall here. So if I were to put somehow an infinite wall here, which went like this, so this would be the bottom of the well and an infinite well going up like this, I would get, okay, these states corresponding to these things, and they would have that much energy. So E minus V0 would have, remember the particle in a box energies, they are exactly these things. Okay? So what is happening here is if I am sending the particle at one of these energies, it is coming in with a wavelength which just becomes in such a way that the wave function becomes 0 here and then continues on, becomes 0 here, and then continues again. Somehow it doesn't feel the barrier. Okay? You have some sort of resonance in which this wave is coming in with just the perfect wavelength so that it hits 0 here where the boundary is, then continues with a different wavelength, okay, but becomes 0 here, and then continues with the original wavelength. So for those special wavelengths, for those special energies, the particle doesn't see this barrier. Okay, that's just the wave nature of the particle. That if you have just the right wavelength, the particle just moves through. It's just very similar to the optics case, where you'll have, again, certain nodes at certain places, in which the electromagnetic wave will just, okay, go through it. Yes? Is there a way to find a wavelength? Well, the wavelength is actually just this distance. Okay, so it's either this distance, half of that, or 1/3 of that, but it corresponds to the wavelength of the particle that's moving in this region. Okay, so it must have an energy E minus V0, okay? It must have an energy E minus V0, and that must correspond to the wavelength associated with the width of the barrier. Yes?
Why when we multiply the A with Q, we end up with N times P? I couldn't understand that one. At the last line.
Okay, I want to find where T becomes equal to 1. Those are points where sign becomes 0. So sign becomes 0 when QA is equal to N pi. Okay, so N pi is equal to Q times A.
I think it was.
Okay, that's it. Yes?
Can you also talk about what is the speed of the tunneling?
Speed of tunneling. Okay. Let me tell you this. There are, again, some ideas that the tunneling is an immediate effect. It really isn't. You can write all of these things in terms of retarded Green's functions. So you can always get finite times out of these things. But you see, we are now looking at the full wavelength, which extends from minus infinity to plus infinity. To find the time that it takes for a particle to reach from one side to the other, there are many techniques, But the safest thing to do is to take something like a Gaussian wave packet, moving here with some initial momentum, and just calculate this using the time-dependent Schrödinger equation. Okay, so you can do that numerically at least. And of course, it will depend on the wavelength and all types of things. Okay, but just in case you hear this someplace that tunneling is an immediate effect, it really isn't. Okay, it's not an immediate effect. Yes.
When this when energy becomes V0,
Mhm.
how this transmission coefficient equal to this value?
Which value?
This graph.
This graph. Okay, I just tried to plot this more or less. Okay, so at certain points, this term is going to be 0, so it's going to be 1, and at other points, it's going to be less than that. And if you look at the limit in which, okay,
Isn't it goes to infinity at E equal to V0?
no, you want E equal to infinity. When E goes to infinity, okay, then you see this term disappears and T goes to 1. Okay, so T goes to 1 for large energies. Okay? At other points, obviously, you have to put in values and see what happens.
Actually, I asked when E equal to V0.
Oh, when E is equal to V0. Okay, when E is equal to V0, let's see, when E is equal to V0, this term is 0. So this becomes infinite, so T becomes 0. So I may have made a mistake here, okay? I know that it's not 0 at that point, okay? So when E is equal to V, but I also have something in the numerator. Let's see, when,
Also, Professor,
just
you
a
also
minute.
depend on-
Yeah, this goes to 0 also, so probably not. Okay, so when they both go to 0, this ratio is probably okay. All right. Yes.
Can you talk about those resonance frequencies for the case where E is less than 0?
No, because there you don't have a wave anymore. Okay, the solution to the problem is no longer a wave, so it's not a resonance.
So there is no tunneling when E is less than V0.
No, there is tunneling. Okay, there is tunneling. That
Time is
there is no
resonance.
resonance. So
Okay.
T is always less than 1. Okay, so there is a current. In fact, this is an important effect. Okay, so let me just take some time to talk about the consequences of this. One very important consequence is known as the tunneling microscope. Okay, this is also important locally because one of the very earliest tunneling microscopes were actually built in this department, in Bilkent physics department. So the Professor Ahmet Oral now, after the Nobel Prize was given to the tunneling microscope, in a few years he produced a number of tunneling microscopes here in Bilkent, and now he has a company selling these things, so turned it into a business. Okay, the tunneling microscope is something that you look at surfaces of materials. So you have some surface, okay, and you want to see, okay, it doesn't have to be that regular. In fact, if it's more irregular, it's more interesting. Okay, so this is the surface of some material. Okay, so this is some surface of the material. And then you also construct the sharpest tip needle that you can construct. Even the sharpest needle that you can construct is not very sharp. Okay, so it has very irregularities. Okay, so these are the atoms on a tip. Okay, so the way Ahmet Aral used to do it is he took a very thin wire and broke it. And when wires get broken, they break in some very irregular shapes. Okay, so what you have here is a low energy region. So if I just sort of try to plot roughly the potential as a function of this direction, so let's call it x again. So until here, I have a relatively low potential. And then I get this region, vacuum, outside, which is high potential. And then inside the material, again, it's low potential. So what you can do is you can send electrons, okay, now in this direction. Okay, so this is now the E. So we have turned everything 90 degrees. And you shoot electrons. Now, you stay in this regime because that's the regime in which the amount of transmission is very sensitive to the potential difference and the width of this barrier. Okay, so you bring this down very slowly, okay, using these piezoelectric transducers. You bring it very slowly towards the surface until a current starts to flow. Okay, so that current is the tunneling current through the barrier. Okay, and once you find that current, then you start moving this around. Okay, so you move this tip towards the left, and then all of a sudden the current starts to increase because you are now very close to this atom. So you have to take this back a little bit so that it doesn't hit into this atom. And then once you're over it, you bring it down, etc. But you can really sense by the amount of current that's passing through from the tip to the material what you have on the surface. And this has atomic resolution, so you can see individual atoms. Okay, so this thing has developed to a point where you make these tips very nice and push these things around. You may have seen the Turkish flag that was made by pushing atoms around on a small substrate, etc. So this was a success story for us for some time. Yes.
Isn't this called scanning electron microscopy?
Yes, scanning tunneling microscopy. Scanning electron microscopy is used then. Is done with an electron beam. Okay, so electron microscopy is quite old.
Also, I was thinking about your comment about the velocity. If the particles are not going face to face instantly, can you explain how for example, alpha decay happens with tunneling?
Well, okay. Alpha decay is another type of problem. It is, again, that's not instantaneous. There's no reason why. Okay, so let me just comment on alpha decay. Alpha particle is a helium-4 nucleus. Okay, so it is 2 protons and 2 neutrons. Okay, so you have some nuclei emit alpha particles. Now, this was a puzzle before quantum mechanics because you had these, okay, so what does the potential look like? Again, we are drawing a model potential. Suppose I have a nucleus. So the nucleus has lots of plus charges, right? It has lots of protons. But then there's this strong force, okay, the pions basically, which hold the protons and the neutrons together, okay? And they, okay, that force means that there's a lower potential energy for these nucleons so that they stay in the nucleus. So if I just sort of very schematically try to draw what the potential energy curve is, there's some, so this is the radial distance, this is the radius from the center of the nucleus. So you have some low energy, okay, which keeps the nucleons together. And then you have, okay, the Coulomb force, which is actually basically it would go to infinity normally. Okay, so this is the Coulomb force, Coulomb potential, 1 over Coulomb potential. And the protons and neutrons of the atom are inside this well. Okay, so they live very happily inside this well produced by the strong interactions. And if you want to hit this nucleus with a proton from the outside, okay, with a plus charge, okay, it will try to come near the nucleus, but because of the Coulomb force, you are going to get a very strong repulsion. Okay, so in fact, if you look at the energetics of this, okay, I don't really know the numbers, but so this is tens of mega electron volts. Okay, so that's the order of this barrier. And then the barrier just falls down. Okay, now, for some nuclei, this is not the most stable form. Okay, for some nuclei, if you just take out an alpha particle, okay, so I'm going to draw something here. This is of the order of, well, I don't know, 8 or, okay, certainly less than 10 MeV. Okay, energy. If you just put an alpha particle here, proton, proton, neutron, neutron, if you separate an alpha particle from the nucleus, then that corresponds to a lower energy configuration. It's a lower energy. And because of that, this object would rather be outside, because then the energy difference will come out as a kinetic energy. So you can actually calculate this. You look at the mass of this, mass of that, differences in mc squared. The difference in mc squared will be the kinetic energy of this if it is released. So what happens is this object here then tunnels every once in a while from this nucleus. Okay, this is called the alpha decay. Okay, now this was a puzzle because people knew that they cannot approach this nucleus because they had to use tens of millions of electron volts in order to get into the nucleus. But what's coming out is few million electron volts. Okay, so they were surprised. Where did this come from? Okay, so the question was something like, we are walking near a building, a very tall building, and then something falls from the building, and you expect it to come down with an energy, okay, commensurate with the height of the building, but it's just a small tap on your shoulder. Okay, a small energy, although the barrier is very high. So you can analyze this system because, okay, so this is a particle in a box state, so it says state like this. Okay, so it's incident on this barrier. And then every once in a while, okay, you get a particle out. Okay, so it doesn't happen instantaneously. Okay, the rate at which these things come out depend on what this energy is. So it's different for different materials. It will be different for beryllium. It will be different for polonium and such things, yes.
What I don't understand about not being instantaneous, if you have charges with the Coulomb force, if they are infinitely close to each other, and if it's passing at some point, it should be at the same point, how the energy doesn't blow up to infinity, like.
Why should it? This is not infinitely thin. This is actually something like 10 Fermi. One Fermi is 10 to the minus 15 meters. Okay, so it's small, but it's not zero. Okay, so if you work in nuclear physics, this is, you may say, well, this is even a big nucleus. I don't know. It depends on. Okay, other question? Yes.
Hocam, for the wave function of the protons inside the nucleus,
Mhm.
they will be present outside of the nucleus as well, right? So when we say tunneling has occurred and alpha decay has occurred, we mean that the wave function collapsed outside of the nucleus.
Well, okay. Again, this is a very simplified version of what's going on. Now, since you have this, okay, region available to this energy state, normally we wouldn't call this a bound state, right? So if let me just simplify this. Suppose I have a potential well which looks like this, okay? So suppose this is going to be equal to infinity here, okay? But on this side, I have something like this, okay? Now, if I ask you for the bound states, what will the wave functions look like? Okay, so I can put here nice sine waves and cosine waves. But over here, I'm going to get these exponentials. And then over here, I'm going to get, again, flux of particles going towards the right. So this is not a bound state, okay? It has, it's not, the energy here is higher than the energy at infinity. So what these states like these are called metastable. And metastable states are such that it's a very good approximation to assume that this is an infinite well. Make your calculations as if this is your real potential. But then after you make this calculation, okay, now you go back and say, well, okay, I really have this barrier here. Okay. Now, what is the rate with which this is going to escape? Okay, so I have here the standing wave associated with, okay, the nth energy level, and that nth energy level is going to produce something like the problem that we have here. It will act like an incident particle on this barrier, and from that you obtain what the rate at which the particles come out. Usually this is a very slow process, okay? So radioactivity is a macroscopic process. The lifetimes can be, okay, milliseconds, but they could also be very long, okay? Hours, years, whatever. So it's an extremely slow process. So this tunneling process is very slow, and then you just calculate what that rate is.